So, how do you even begin to dig for gold in some of the wettest, most geologically chaotic places on the entire planet? You're not just fighting against rock and dirt. No, you are in a constant high stakes battle with one of the most powerful forces on Earth: water. So, how is it done? Let's dig in. To get to those incredibly rich gold deposits that lie in these wide river valleys, you can't just, work around the water. You have to control it completely. And in a lot of cases, that means doing something that sounds almost impossible: literally moving an entire river.
So here's our game plan. We're going to break down this massive undertaking. First, we'll get a feel for the extreme environment. Then we'll see how engineers try to predict the future, how they build their defenses, fight a hidden battle underground, and finally, how they plan for what happens after they're gone.
Okay, so let's start with the environment itself. Because we're not talking about just any river valley. This is a true battlefield of natural forces.
A lot of these mining operations are in what's called an active orogenic belt. Now, that's a fancy term, but what it really means is a place where mountains are still being formed. They're actively being pushed up from the earth. And that creates this perfect storm of steep slopes, insane amounts of rain, and the constant threat of flash floods. It's one of the most dynamic environments you can possibly imagine. Now, here's what's really key. In most mining, you're thinking about geology, right? The rocks. But here, everything changes. As the source material puts it, hydrology, the science of water, is the number one thing. It's the dominant control. It dictates absolutely everything. You get the water wrong, and you're facing a catastrophic failure. So, if water is enemy number one, your first job is to do some serious intelligence gathering. You have to know exactly what you're up against. We've all heard that term, right? 100-year flood. But what does that actually mean for the engineers who have to build the defenses against it? How do you possibly calculate the size of a disaster that, by definition, almost never happens? Well, the answer is statistics. Engineers use formulas like this one. They look at historical data, like the average flow of the river and how much it tends to vary, and they use a statistical factor to project forward, to estimate the sheer power of one of these incredibly rare, high-impact flood events. And this is the part you really gotta understand. A 100-year flood doesn't mean it happens once every century on the dot. It's a risk assessment. It means there is a 1% chance of a flood that big happening in any single year you're operating. 1% might not sound like much, but over a 20-year mine life, those odds start to add up. And the numbers, they're just mind-bending. In one case study from Papua New Guinea, that 100-year flood event was calculated at nearly 1,550 cubic meters per second. To put that in perspective, that's enough water to fill an entire Olympic-sized swimming pool in about 1.6 seconds. That is the kind of force we're talking about. So once you know the size of the monster you're dealing with, you can start to build the armor. This is where the really heavy-duty engineering kicks in. And this drawing shows the core strategy perfectly. It's basically a 1-2 punch. First, you dig this enormous, super carefully engineered diversion channel. Its job is to take the entire river and route it safely around your mine. Second, you build this huge wall of earth. It's called a berm, and that's your last line of defense, walling off the mining pit and keeping it dry. But listen, you can't just dig a big ditch and hope it works. That diversion channel has to be designed with incredible precision. You have to get the slope just right, just like the natural river. You've got to control the water speed so it doesn't just tear the new channel apart. And you have to stop it from eroding or just filling up with sand and gravel. It's a really delicate balancing act with immense forces. And it's not all just about giant earthworks either. For day-to-day safety, there's a whole toolbox of other gear. From things like these big inflatable dams for temporary water diversions, to these heavy-duty steel trench boxes that protect workers when they're digging in that wet, unstable ground. Okay, so you've moved the river, problem solved, right? Well, not even close. Now you've got to fight a second, sneakier battle against the water that's already in the ground all around you. This never-ending job is called dewatering. It involves a whole combination of tactics. You've got trenches around the perimeter to catch runoff, powerful pumps sitting in the lowest part of the pit, and sometimes even complex well point systems that actually suck water out of the ground to lower the water table.
Let's just run some quick numbers so you can see the scale of this problem. A typical open mining area that you need to keep dry is maybe 20,000 square meters. Think about the size of 3 soccer fields.
Okay, now let's say you get just one heavy storm, maybe 80 millimeters of rain, just over 3 inches. That single storm just dumped 1,600 cubic meters of water right into your worksite. So to get that water out and get people back to work in just 2 hours, your pumps have to be able to move more than 200 liters of water every single second. And remember, that's just to handle one storm, on top of all the groundwater that's already seeping in. And really, it all comes down to this simple, brutal fact. There is zero room for error. That's why having redundant systems, backups for your backups, is one of the most fundamental principles of site safety. Because if your pumps fail, your mine floods. It is as simple and as devastating as that.
All this incredible engineering isn't just about surviving the next storm. It's about planning for decades of operation and for what comes after, all in a very uncertain future.
Yeah, a truly responsible design has to look way down the road. That means you have to plan for climate change, which could bring even more intense rain. You have to assess the risk of earthquakes triggering landslides, and this is critical, you have to have a rock-solid plan to restore the entire river valley once the mining is finished. And in the end, it really does come full circle. The same incredibly complex computer models that they used to design the diversion channels and defenses, they use them one last time to make sure that when they put the river back, it's left in a safe, stable state for the long haul. All of this leaves us with one last really big question. We've seen the incredible science and the mind-boggling engineering it takes to even attempt this. But can all this human ingenuity truly, and more importantly, sustainably, balance our immense demand for resources with the raw, untamable power of the natural world?